got the goof troop on the scene here, so this is
not the 18.
If it doesn't work, it's the other person's fault.
I'll take it.
But if it works, then it's on the student.
Yeah, students, incoming first years next year will thank you for. It's like, I don't know, we caught kind of the door and just heard Bob talking for 3 hours. It was good. All right. So, as a conceptual summary, where we left off last time, talking about our repeated measure ANOVA designs. Okay. When we just have participants observed only at one time for our between group designs, right? What we have is a lot of individual differences that's just due to people being different. That gets designated the error term, right? And what that does is that makes that term a lot bigger. That error term is going in the denominator of all our F statistics. And so tomorrow, if my error term is bigger and it's going in the denominator of my F statistics, what does that do to the likelihood of me identifying evidence for effects? If my error term in the denominator is bigger, if I'm dividing something by a bigger number, decreases it, right? And so what we want to do, it would be nice if we could in some way capture those individual differences. When we go through and we look at people over a number of repeated assessments, what we're able to do is we can capture those individual differences, measure the extent to which the variability we're seeing in your data is due to just the fact that different people are different. And what we can do is we can section that off, take it out of the error term. We can model it and say, it's not just random error, this is, well, it is random error, but it's between differences error. And if what we're interested is changes in a repeated assessment over time, we can set that out and say that's not part of what we're looking at here, okay? The more variability we get across our participants, so the more individual differences that you get, the stronger the correlation is going to be between these interventions, okay? Again, this has to do when we're thinking about correlations. If we have restricted range in terms of our correlations, what does that mean if we're talking about restricted range? What's that?
Like it can only be a value between -1 and 1.
It can only, okay. So yeah, it's the bounds of our correlation, right? Anybody heard of restricted range used in a different context?
It's about this like spot that happens in moderation when you have only one range of data of the two variables where it works.
Yeah.
And after that,
you're getting there. Let's say this is a good example. Think about our GRE scores associated with success in graduate school, right? And let's say we have some objective measure of success in graduate school. One of the arguments against GRE scores is people say, well, GRE scores don't predict a lot, right? And if we go through and we look at the correlation between GRE scores and success, what we find maybe something like that, right? I don't know, right? It's not super strong correlated, and so what we've got is an effect like that, okay? What's a potential problem of this study, looking at GRE scores and success in a doctoral program?
You're just looking at the range of the GRE scores, which is limited, so if you have two people that score the same thing, it's probably unlikely, given this, that their success is going to be the exact same.
Let's say my low end here is a score of 300 and my high is 330, okay? I'm only capturing a very narrow band of GRE scores in this. If I were to go through and run a different study, right, where I had GRE and success in a hypothetical group of individuals who all got into doctoral programs, same sort of level of doctoral programs, irrespective of GRE scores, probably what we would see is maybe something like this, where we do have a pretty strong association, right? But if I only look at this section, it doesn't look like there's any association at all, right? If I've only got this piece, that's kind of what that looks like, right? And so when we talk about restriction of range, this happens if I'm only sampling people who are high in some trait, right? I'm only sampling people who are very, very high in self-handicapping. And so I only say that, well, self-handicapping doesn't look like it's associated with GPA, because I just got a bunch of people who are self-handicapped who don't have very high GPAs, and so it doesn't look like much of anything. But if I looked at the whole range of self-handicapping, now I see, oh, there actually is a really strong association. I just super zoomed in on the one window where now it just looks like a cloud of dots, right? And so when we're thinking about our repeated measures designs, right, the more variability that we have in our participants, the more sort of they're jumping around, the stronger the correlation is going to be between our treatments, and the more powerful our repeated measures design is going to be, okay? I've done some work with psychophys stuff. Again, tomorrow you've done psychophys stuff before, right? And if we're looking at things like skin conductance, we've got a very, across repeated assessments, super, super strong correlations there, right? Because you've got a closed physiological system, like wherever I start, like I don't have, like my body's not able to just randomly jump around all over the place, right? So if I measure for a 2-minute epoch at this point, and then another 5 minutes later I run at a 2-minute epoch at that point, those values are going to be correlated probably like 0.9 with one another, right? So they're super, super highly correlated, even though people start all over the place. Some people have very low skin conductance, sometimes people have very high skin conductance, but it doesn't matter where I start, because we're all changing the same way, really, really strong correlation. And so repeated measures designs with measures that are very, very highly correlated are incredibly powerful and really, really able to start to tease apart some of those sort of changes across time, okay? So again, the idea with our repeated measures assessments, what we're looking at in our one-way designs that we've talked about to this point, we're wanting to see, are there differences across in mean values across repeated assessments? And what we're doing is we're capitalizing on the fact that everybody is serving as their own control. And so we can take and measure that individual difference, pull it out of our error term, and now all of a sudden we've got a very, very pure and very powerful test of whether or not we're seeing changes over time. Okay. Questions about the design, how this is all set up? Okay, cool. So we're going to work with a couple of different data sets that are different in important ways. Our first one, what we've got is a group of individuals, large group of individuals who are being treated in an inpatient unit, okay? So these are individuals who are seeking inpatient psychotherapy, and we've got four assessments of depression. We've got people when they first come in, and then over the course of 6 weeks of treatment. Every 2 weeks, we've got a measure of depression here, okay? And what are we hoping, at least probably, Alicia in this set, is going to happen if we're measuring depression scores over 6 weeks? What would we be hoping to see in terms of the pattern of those depression scores?
Decrease.
Hopefully they're going to decrease, right? Hopefully we're not just wasting people's time not doing anything. Hopefully we're going to see patterns decrease there, okay? Then we're going to have a second data set where our question here is whether or not, what are people's reactions to trauma, and how likely are they to provide support to survivors of different types of stressful events. And here what we've done is we brought people in and had them read 8 different vignettes. Right? And this vignette says, Chris M. was, or whoops, Chris C. Sorry, Chris C. Chris M. You can have some other disaster befall you. Chris C. was deployed to Afghanistan and has come back, and now he's doesn't want to talk about things, and he's aware of people being around him or something like that. How willing would you be to maintain friendship with Chris C., right? And so we read that vignette, we rate how willing, on a 0 to 8 scale, how willing we are to provide, maintain friendship with Chris C. And then we say Chris M. Was involved in a terrible hurricane in Florida.
I was never
destroyed.
Well, I'm going to Afghanistan all the time.
So you were bummed to be there in the first place, and then your house got blown down,
That's
right?
true.
So now you're sort of super hyper vigilant things. How much are we willing to provide support to Chris M? And so looking at different things. And so the idea is like, do we see differences in willing to provide support to hypothetical individuals who have been through different types of events, right? Now what we did here, when I collected these data, in my mind, when I was thinking, well, what I'm interested in is how people respond to different types of things, right? What are my options here? Well, one, I could have had people come in and just respond, different groups of people respond to these different vignettes, right? I could have done that, right? Why didn't I do that?
You don't really have a control at that point.
What's that?
You don't really have a control for an individual specific.
I don't have any control, right? How many people am I gonna have to collect?
A lot.
A lot, right? I've got essentially 8 different groups. How many people am I gonna have to get in each group in order to detect, find evidence of non-zero differences? I'm gonna have a massive sample, right? It's not feasible. But what we can do instead is just have one potentially large group of people come in and give them different vignettes to go through and respond to, right? So I rate motor vehicle accident and then combat to infidelity and sexual assault, so on and so forth, and have people, the same group of individuals, rate each one of these vignettes separately, okay? Now we've got a repeated measures design that's much more powerful. What's the limitation of the repeated measures design here? Yeah.
Exposure to the vignettes over the course of time.
Yeah, right. If I go through and I ask you how impactful, right, having someone who's had a partner who's been unfaithful, right? That's a objectively stressful situation, right? But if I set that, juxtapose that against, say, combat exposure, now all of a sudden, boy, we've got contrasting, we've got carryover effects, right? Which is one of the things we're concerned about with our repeated measures designs, right? So what can I do to address the carryover effects in this study if I really feel like I need to have a repeated assessment?
Scramble.
Scramble,
I don't know
right?
the word.
What do we call
Counterbalance.
scrambling? Counterbalance, yeah, right? So what we did here is we scrambled them. I probably went overboard, but there's a lot of unique combinations you can have across 8 different vignettes. I probably had like 30 different orders or something like that. And then we had to go through and like put all together the packets all in different orders and go through and do. But what we did is went through and counterbalance. And so there's still fuzz going on, right? Because no matter what I do, my subsequent ratings of how impactful these things are always going to be influenced by what I saw before, right? But the idea is hopefully by counterbalancing these, what we're seeing, if we're seeing differences in people's ratings, aren't due to what they saw before, because what people saw before was all scrambled around, and we can't say that, use that as a plausible alternative explanation for why one thing may be higher than the next, because everybody saw them in a different order, right? So the upside is that it accounts for carryover effects, or at least it addresses it. Downside is it does add additional kind of variability and sort of stuff going on, okay? So these are going to be important. 2 different sets. This one, ordered means, does the order in which we're assessing depression scores, does that have an impact on how we think about these data? Absolutely, right, because they're happening in time. Does the order of events here make a difference? No, it doesn't. And so this starts to change how we start to go through and take a look at and start to tease things apart down the road, okay? All right, so let's go through and work with the ordered assessment first. So open up the ordered means, okay? So I gave you last week a sheet that says in-class example, one-way repeated measures ANOVA. You'll have that with them. We're not going to go through and actually run through all the screening with this because it's not a good use of our time. So it's stuff that we've done in the past, but we'll go through and talk about screening these data. These data actually turned out to be fairly okay with stuff. We'll actually go through and do a screening with our mixed factors ANOVA, so we get an opportunity to go through and practice using SPSS to go pull things through, but we'll take a shortcut on this one. Got it. Okay, so again, and Sean Ignacio, with the screening, like this is the sort of, I don't give you many templates. This is a template. Use this template. I mean, change sort of your interpretations around so that they make sense given the data, but the overall structure, this is just a way to keep things organized, and it helps me when I'm looking at your screenings to see if you've got the right things, right? So for this set, we've got a one-way repeated measures ANOVA, where we're looking at depression scores at intake 2 weeks, 4 weeks, and 6 weeks. What we find in our data set, if I go through, I take a look at it, and I sort BDI 1, sort BDI 2, 3, and 4, I don't have any missing variables. I got full information on BDI 2 scores, right? So, because in my one-way ANOVA, that's the only thing I'm concerned about. We say we got no missing values. If we go down through, we take a look at min-max, they all fall within the range of BDI 2, so we're good to go there, right? So no missing values, no evidence of problematic values. So we're going to proceed with analysis of the full set of 388. Then what we're going to do, because we have a repeated measures ANOVA, right? What we want to do is take a look at the distributions at each assessment point, right? And actually, when we go through and take a look, they look reasonably good, right? So at intake, we've got skew and kurtosis values of negative 0.08 and 0.64. At week 2, skew is 0.73, kurtosis is negative 0.13. Week 4, skew is at 1.06, kurtosis is 0.57. Week 6, we've got skew of 1.5 and kurtosis of about 2. And then going down through and talking about sort of the histograms and the box plots, kind of describing some of those. What are we seeing in terms of our distributions as our measurements continue? I think we should.
More skew and more kurtosis.
Yeah. So as we move forward, our data are doing different things, right? It's looking at skew is getting incrementally larger. So by the time we get to week 6, it's still not bad, right? It's not anything that we would be concerned about, right? Yeah, Ignacio.
Which are which is the range you would be acceptable for the students?
Well, and that starts to get sort of, that's a good question, right? Whoops. What is, for our means-based analyses, what is our distributional assumption? Yeah.
Normal distribution.
Normal distribution of what? Distribution of sample means, right? So do we care about the actual observed distributions?
No.
Yeah, we might not, right? Again, what are the 2 conditions under which our distribution of sample means starts to become normal very quickly?
Increasing the sample size.
Increasing sample size, and what's the other one? Population is normal, okay? So I don't know if the population of, in a hypothetical population of people who've gone through 6 weeks of inpatient treatment, I don't know that the distribution of their BDI scores is normal. Probably not, right? But how many people do I have in this sample?
Almost 400.
Close to 400, right? So my analyses, as long as I don't have any other things going on, my analyses are going to be pretty robust, right? Because with a sample of 388, distribution of sample means is going to get normal real fast, right? But what we want to do is also think about, and this is part of our screening, take a look and think about what's going on in our data. Like, are there things that are going on distributionally that are making sense? And what we're seeing is when we start everybody off in treatment, things are looking pretty normal. But as we start to progress through treatment, things start to get increasingly positively skewed. Yeah.
That's because you would, I mean, at least you would presume that it's due to people improving in terms of.
Beautiful, absolutely. Some people are going to get better. Hopefully most people are going to get better, but we're going to have some people who don't get better, right? And if we go through and we take a look at the data and we start to see as we progress through treatment, that distribution start to skew out to the right, basically what's happening is for the majority of people, treatment is working and scores are getting lower. But we've got some people who it's not. They're just kind of high levels, and so we start to skew that out, right? Now that doesn't have anything to do necessarily with our analyses, but it is something that starts to become important when we're going through this screening process, not just doing it for our health, right? To try and understand what's going on with the data. Are the data doing things that make sense given sort of the study and things that we know what are happening? In this case, it does, right? So in general, with a sample of this size, starting to see some level of non-normality. So Ignacio, to get to your question, usually kind of rule of thumb is skewer kurtosis less than 2. But it really depends on your sample size, it depends on a lot of stuff. And even if I have a skew of 1.9, right? And this is the mistake people make sometimes. Well, I got skew 1.9. Well, 1.9 is not 2, right? And so I say, well, my data were approximately normal, skew is 1.9. If I graphically look at a skew 1.9, does that data look normal? No, it's obviously skewed, right? And so we have to be careful about how we're talking about things. I can say that these data, the level of skew or deviation from normality in these data do not appear problematic given the assumptions of the test. But I wouldn't want to try and say, oh, it's fine, it's normal, when it's clearly not, right? So but we'll talk, that's kind of a general rule of thumb, but as we sort of get into regression, we'll talk about.
So, and is there a way that Shapiro well is telling you is normal, but the skewness is telling you is not normal?
What's that now?
What about if you are running this Shapiro or Shapiro?
Okay, so this is the other thing too. Yeah, this is another thing too. So oftentimes what people will do is they say, well, are my data violated normality? And so I'll use a test like, is it Shapiro-Wilks, something, I can't remember what the test is. And I go through and I run this test, and what I find is I have significant skew. If I say that I have significant skew, what does that mean? What's that?
It's not normal.
Well, technically, what does it mean? What does anything mean if I say it's statistically significant? Right.
For that test.
For that test. And what is probably the null hypothesis for that test?
0.
That it's 0, right? So what that test is telling me is that the skew of my data is not 0. Do I care if my skew is not 0? No, right? The assumption isn't that my skew is 0, right? If the assumption of the test was that the skew is 0, I would never run any tests because there's no, real data don't have a skew value of 0, right? And what happens is my sample starts to get larger and larger and larger. What does that do to the power of my test? It increases it, right? So if I've got this sample of close to 400 people, and I run a test, and I find that my data is non-normal because it has significant skew, we see is people freak out and then start doing a bunch of weird-ass transforms on their data when you don't need to. Because the assumption isn't that it's 0, right? And if I've got a big group of people, any deviation, my skew could be, I have a skew of 0.05, right? If I got a big enough sample, that's going to come up as statistically significant, right? Does that mean anything useful to me? No, right? Because my assumption of my test isn't that this observed data has a 0 skew. But that's what that's testing, right? So what will happen is people will sort of use that to test the assumption and then sort of start making corrections for something that you don't need to correct for because the assumption isn't that your data is perfectly normal. It just sort of has to be kind of within bounds, right? And then particularly if I'm using sort of for regression analyses where I should have large samples, and when I do have large samples, minor deviations are going to come off as statistically significant. And so now what I've gone through and done is done a bunch of transformations and things that aren't necessary and complicate the interpretation of my data. Because now instead of age, I've got the log transform of age. I don't know what the log transform of age means. And even if I log transform, it's still probably not exactly 0 anyway. And so now I've introduced a whole bunch of things that I didn't need to introduce in the first place. So this is why, as we're going through screening, we'll do an example. I'm going to get farther along. One, to go through and take a look at our data and say, okay, what's really going on? To what extent is this violating our underlying assumptions, and to what extent is this going to be problematic for our inference? Okay. We'll get lots of experience with this. Okay. All right. Other questions with this? All right. So distributions, extreme values, outliers, minimal evidence of extreme values in intake, acceptable. At week 2, week 4, we've got a case number 47. It's a little over 3.3 standard deviations away from the mean. That's starting to get notable, right? Week 6, we've got 1, 2, 3, 4 values that, and some of these are getting pretty extreme. Case number 50, case number 3182 has a BDI score of 52. That's over 4.5 standard deviations from the mean, right? Chrissy, these are notable, right? Anyting anytime you got a point that's over 4.5 standard deviations away from the mean, that's pretty extreme value, right? We might even call that one a true outlier. Are we worried about it with this set?
Not really.
Why not?
We have a big sample, and also I think that it's important to include cases that the treatment may not have worked as well.
Yeah, absolutely right. So again, this is another thing people overreact. Like, oh, I've got an outlier. I've got something that exceeds 3 standard deviations from the mean, and so now I'm smoothing things. I'm transforming things. I'm dropping cases. Well, that starts to become problematic because if my question is does my treatment work, and I start throwing out all the people who the treatment didn't work for, and I'm pretty excited about the results, but what I didn't do is account for people in the population who this isn't going to be impactful for, people who might even make symptoms worse, right? And so we need to go through and start thinking about, again, yeah, these are big values, right? But what's the impact going to be on our data? With a sample of close to 400 people, one person hanging out on the tail probably isn't going to drag that mean out too much. Now, if I have 20 people and I have someone who's 4.5 standard deviations away, then I'm probably going to be a little bit more concerned. Maybe then if I have 20 people who I've followed, maybe then I do need to start thinking about transforms and things along those lines, right? But for these data, given the sample size, given that our assumptions have to do with the sampling distribution of the mean, we're probably going to be okay. Talking about homogeneity of variance, right? We're going to see that we don't get homogeneity. We don't get a Levine's test for a one-way repeater measures ANOVA. SPSS won't give you a test of homogeneity of variance across repeated assessments. So what we're going to use is our Fmax, right? We talked about Fmax a little bit. Looking at the ratio of our largest variance to our smallest variance. Make sure you're looking at variance, not standard deviation. For a balanced design, right? And Tabach and Fidel, Howell will talk about balanced design about being 4 to 1. That's pretty unbalanced in my mind, but that's, Fmax is high as 10, but we've got a straight repeated measures design. Can we have unbalanced design here? No, it's the same people in each cell, right? And so Fmax less than 10, that would be pretty, you're saying the ratio of variance of your measures at the smallest variance time point, the largest differs by a magnitude of 10. That's pretty intense, right? But whatever. Here, our Fmax is 1.76, suggesting that our variability, or the variance of our depression scores across repeated assessments is fairly comparable, so we're not too worried about that. And then we have sphericity, right? And we're just going to say violation of sphericity is assumed given the study design. We're not even worried about it, right? We're just going to assume that's a problem. So if we go down to our recommendations, we've got evidence of increasing skew, evidence of extreme values in depression, assume violation of sphericity, and so then what we're going to do, Sean and Ignacio is trying to tie all this together in sort of a brief recommendation. Here, this is where you're playing the role of statistical consultant. I've given you these data and say, hey, this is what I want to do with it. You go through and say, all right, well, this is what we're going to say about this, right? So we say, preliminary screening indicates increasing skew across assessments. However, Observed violations are unlikely to impact underlying assumptions of sampling distribution given the number of participants in the sample. Basically saying, we've got a big sample, yeah, we are getting some skew, probably doesn't matter, right? Increasing skew distribution is also consistent with expected reductions in some but not all patients over the course of intervention. Extreme values, while notable, also minimal concern given the sample size. Recommend use of greenhouse geyser correction for homogeneous tests given presumptions of violation of homogeneity or violations of sphericity. So overall, do we have too many concerns with these data? No, right? Are they perfect? Not even close, right? But this is real, actual applied analyses. And so at the end of the day, this is probably about as good as your scores are going to get in terms of overall stuff. Okay? So questions about how we went about screening for the one-way repeated measures ANOVA stuff here. Okay, cool. Let's jump in then and run our analysis. So we've got your handout. We're going to pull one-way repeated measures ANOVA with ordered means.
Quick question. We have 6 weeks in the description, but we have 4 weeks in the data set.
Oh, so yep. So BDI 1, 2, 3, and 4, these are just our 4 assessments. BDI 1 is intake, BDI 2 is 2 weeks, BDI 3 is 4 weeks, BDI 4 is 6 weeks. So there's just a difference in sort of what the variable name is and what it actually represents. Okay. So what we're doing here is we're assessing people on a bi-weekly basis. Okay. So what we're going to do is we're going to go up to Analyze, and we're going to go to General Linear Model, and we're going to go down to Repeated Measures. Click on that. And so what we're going to have first here is it's going to ask us what our factor is. Our factors are going to be our repeated assessments. So the name, you can name it whatever you want, but what you probably should do is name it something that makes sense in terms of your repeated assessment here. So what did I name this? I named this repeated measure session. So measure this session, and then how many levels of my repeated measure do I have? Sally? 4. There we go. We got 4 repeated assessments, and I hit Add. Okay? Follow me up at this point? I'm going to hit Define. And what I'm going to do is I'm just going to use this to go through and order these up. So I got BDI 1 in the first order, BDI 2 in the second position, BDI 3 in the third position, BDI 4 in the fourth position. Easy peasy. Everybody follow me to that? Okay. So we're just working on a straight one-way repeated measures ANOVA, right? We don't have anything else going on with this, so we don't have to worry about between subject factors, covariates, things along those lines. But what I'm going to do is now I'm going to go down through and I'm going to hit contrast. So if you hit contrast, you'll see what this is doing is it's going to automatically estimate a set of polynomial contrasts for a session. Don't worry about that quite yet, but just want you to see that's where you're looking. If you want a different type of contrast, you can go through and select that here. We're not going to worry, we're just going to leave it at the polynomial for right now. I'm going to hit continue. What I'm going to do is now I'm going to hit plots. Okay, this is going to plot out your different means. So to give you kind of a picture, SPSS is, the plots are garbage, but at least it'll give you a visual about kind of what's going on, right? So we want session on the horizontal axis, okay? And then we don't have anything else to do there, so we're going to hit add. And so that's going to add just repeated measure of session as a plot. I'm going to hit continue. I'm going to go down to options. I'm going to request descriptive statistics, estimates of effect size. Click homogeneity test, even though it would not give you one, but just do it anyway. And then hit continue. Okay. So, everybody follow me up to this point? So I'm going to hit paste and drop this into a syntax file that we can later use, manipulate, so on and so forth. required to do this. Intense. Okay. First thing that happens, very top of the mark, it says warning. Tomorrow, do we ever ignore warnings? No, never ignore warnings. Always look at the warning to make sure you understand what the warning is about before you move forward with things, right? Warnings are inconvenient sometimes, but if we're doing good science, we want to make sure that we go through and account for that. And so we say, homogeneity specification in the print subcommand will be ignored because there's no between subjects factors. What this is saying is we request a homogeneity variance test. There's no between group factors, and the Levine's test is a between group test. Because there's no between group factors, can't give us anything, so we just said, hey, you asked for this, we didn't give it to you. So we're not too worried about that, okay? But if we go down through, one thing you always want to do with these designs, as you start to get into more and more complex designs, make sure that your output is giving you what you think you're actually getting, right? So here with our within subject factor, we see our repeated measure of session. We've got BDI 1, 2, 3, 4. Is that what we wanted to do? Yep, so that's looking good, right? We got our descriptive statistics. We got BDI, the mean at intake, 2 weeks, 4 weeks, and 6 weeks. Sally, what's happening? What are we noticing in terms of our mean levels across our repeated assessment? They keep getting smaller. So this is good, right? Even before we jump into our analyses, want to see, are they doing the things that we think they should be doing? Looking pretty good. This is also where I went through and calculated my F max from. If we take, it also looks like my variability is decreasing over time, right? Which kind of makes sense as people start to get better and better uniformly, things start to get tight, versus where the people started were kind of all over the place. If I take 90.55 and I square that, and I take, if I take 12.688 and square that to get the variance, divide that by 9.551, square that to get the variance, it's going to give me my F max, right? It's just the ratio of the largest variance to the smallest variance. That's where I pulled that up.
It's so easy, straightforward.
Yeah, it is. It's nice. You love it, right?
Yeah.
Yeah. Cool. It gets a little more complicated when we get into sort of the mixed design, but so we got that. Then we got a table called multivariate tests. Ignore these, okay? Back in our history, there's a big deal about how we go through and look at repeated measures of designs because we've got this violation of sphericity, right? Multivariate test is one approach to doing this, but it's really not the one we use today. This is basically taking like a ANOVA type design approach to this, but our corrected statistics are going to work fine. So we're going to ignore the multivariate tests here, right? We go down, we see the test of sphericity. CJ, are we going to spend too much time here? Why not?
Because we're probably never going to meet it.
Yeah, we're going to assume that we violated that anyway, okay? And actually, I'm just going to do this, and this is I had you do this on the sheet. We didn't do it here. I'm going to go down. I'm going to go and request my bivariate correlations for each one of these. Okay. So if you're looking at here are your bivariate correlations, and these are on the front page of your sheet. Nick, what are you seeing in this correlation table that might suggest that these data, as expected, have some concern with violations of sphericity?
Looking at the size of the correlations and the associated significance values between one another.
Yep.
They look like all of them are significant.
Okay, they're all significant, right? And so, but we knew that, right? Remember, this is going back. Remember, we've got two assumptions or two different states here of this. So it's technically has to do with our variance covariance matrix. This is a correlation matrix. It's that we took that variance covariance matrix and standardized it. This is what we would get, right? But remember, we had two different characteristics we talked about. The first was compound symmetry. Compound symmetry says that what we're expecting, if our data are consistent, sort of working properly, the variance estimates across each one of these assessment points is the same, right? So we've got equal variances across assessment points. Now, you probably know that I don't know, particularly with a sample of this size, that they would all come up as identical, right? So we kind of got some stuff there. But then remember with compound symmetry, we're saying that the covariance between each assessment point is going to be identical. So the variances are identical, and the covariances between each pair of assessment points is identical, right? And if I say covariances are the same, what's that similar to saying? Covariance is a measure of what?
How much variable X varies with variable Y.
Perfect. How X varies with Y, right? And so we can also talk about if we standardize that covariance, we've got a correlation, right? So by extension, if our data were meeting characteristics of compound symmetry, what would all the correlations in this off diagonal be? The same, right? And they're clearly not, right? Now, compound symmetry isn't required for repeated measures analysis. So our sphericity assumption says that instead, like all the covariances don't have to be the same, but the variances across different difference in variances across all of our repeated assessments are going to be the difference across all of our repeated assessments are going to have the same variability, right? But we know that's probably not going to happen too, because we know that things that are measured closer in time are going to be more strongly related to things that are measured more distantly in time, right? And if we take a look, we see that this is actually the case in this correlation matrix. Correlation matrix is just kind of like a proxy for this, but we see if we look on the diagonal, 1 and 2, measure 1 and 2 are about 0.6, measure 2 and 4, 0.7, measure 4 and 6, or measure 3 and 4, 0.75. Then if I look at my first measurement, my last measurement, correlation 0.38, right? So we're seeing that measurements that are were assessed more closely in time hold a stronger correlation than things that are increasingly distant. So even if we look at this first column here, we see that 1 and 2 correlated at 0.62, 1 and 4 is 0.44, 1 and 6, 0.3. So we see our correlation dropping as we get farther away from one another, right? This is a classic example of the problem with the sphericity assumption, is what we're assuming generally that our repeated measures are all differing to the same extent across no matter which two that you put together. We know that's not how behavior works, right? As we get farther and farther away from where these assessments start to increase in their distance and time, they're going to get less and less correlated with one another, which is why we always assume that probably we've just violated sphericity and then just go straight to our corrected test and not even worry about this. Okay? Does this correlation table kind of help sort of get that, solidify that idea of sphericity a little bit better? Okay, cool. And so this is, looking at measuring depression scores over the course of 6 weeks, right? But even in small, like experimental studies, right? If I'm measuring something in between, say, experimental stimuli repeatedly over the course of like 4 different measurements, and those measurements are occurring, you know, in 2 or 3 different 2 or 3 minute intervals, we're still going to see the same type of thing probably happen and come up here. So want to keep an eye on that. So we're not going to spend much time on sphericity assumption because we're assuming that that's going to be violated anyway. And so now we're going to go down through and take a look at our tests of within subjects effects. Okay, this is the table that you're going to be most interested in 99% of the time when you're running these types of designs, right? That repeated assessment is probably the reason you're doing the whole thing in the first place. And so what we want to go through is take a look at our effective session here. Okay? And Sean, what are we seeing? Remember, we're looking at our greenhouse geyser row here. What are we seeing in terms of our repeated measure of session here in this greenhouse geyser row?
Reducing the degrees of freedom, right? For the greenhouse gas? By that epsilon factor?
Yep, so yeah, we see a correction on my, so you see correction on degree of freedom, and we know that that's what greenhouse geyser does, so that's good. What about just, are we seeing an effect of repeated assessment? What do you think, Ignacio? Yes, how did you know that?
Well, if I'm correct, this is a test to know whether there is a change from one group to the other.
Perfect. Our test of our repeated assessment here is just saying, it's actually sort of, our null hypothesis here is that the mean value across repeated assessments is identical, right? And what we're seeing here is a p-value that, well, it says 0.0, so it's less than 0.001. What do we know about an f value of close to 430? Real big. That's going to be large, right? And if we go through and we double click on that p-value, we see the actual value is 1.42 times 10 to the negative 140. That's assuming that we've done things correctly in terms of gathering these data. These data are functionally impossible given the null hypotheses, right? And here we see an effect size. We're going to talk about that. But for those of you from 50-60, is a partial eta squared of 0.53 impressive? Yeah, that's massive, right? So based on our test statistic, it's suggesting that we have a very, very strong evidence that at least one of these means is different than the rest of the means, right? Okay. So yep, here's our greenhouse geyser corrected test. Here's our greenhouse geyser corrected error, right? We'll ignore our test of our within subject contrast for right now. We'll talk about that in just a minute. Then we've got here a test of between subjects effects. We're seeing, yikes, that's an F of, that's massive. Anybody for $10 million question, what is our test of between subjects effects telling us here? Yeah, Chris?
Differing responses to treatment across.
Yeah. Functionally, like literally what this is saying is that people are different, right? The mean values collapse across assessment points across people is different. They're not the same, right? So if everybody came in and started with a mean value of 20 and ended with a mean value of 5, and each one of the individual, everybody's individual scores across that were all the same, then that would be significant because everybody's the same, right? But it's not, right? And this is what we would expect. This is the whole reason we do these types of analyses, is because we expect that almost any phenomenon that we're measuring is you're going to have wide individual differences, right? This, in the one-way test, is not terribly informative or useful for anything, but conceptually it's interesting to look at. It's just saying people are different. Over the course of repeated assessments, people's average scores differ from other people's scores, right? So just kind of be aware and tuck that in your head as we can go through and talk about other stuff, okay? Here we have our estimate of our marginal means, which in our 108 design is just our regular means, and we're seeing very clear reductions over time. So with our effect here is just saying that, yes, in fact, we have evidence that at least one of these repeated assessments is different than another one. Technically, that's all we can infer from our omnibus test. But if we go through and take a look at our graph, it's pretty clear what's going on there. Okay. People comfortable with our interpretation of our omnibus one-way ANOVA here? Any questions? Okay. Let's take a look at a little bit different set. Pop open your repeated measures for your beliefs.
We close that.
Was it? Yeah, you can close that. Well, leave it open. You'll open it up again. It'll open back up. All right. So same thing with our beliefs data. What we've got here is for all of our ratings on whether or not we would be willing to provide people friendship. No missing values here. So we're happy about that. Okay. So we're not going to worry about screening these data. We'll get into that when we get into mixed factors. We'll do that. So let's just run through and take a look at our just a one-way repeated measures analysis. So we're going to go to Analyze, over to Generalize, General Linear Model, down to Repeated Measures, and we'll call this repeated measure of rating. And how many measurement levels do we have in this tomorrow? 8. Exactly. 8. Add that. And hit define. All right. Now what I'm going to do here, now I'm going to start grouping. So what we did is give people vignettes for events that are probably more consistent with traumatic events and other things that are definitely stressful but not technically traumatic events. So what I'm going to do is I'm going to go motor vehicle accident, combat. I'm going to skip down and go down to assault. And I'm going to go down and disaster and put those in. So I'm going to order up my trauma vignettes first. And then we've got infidelity, chronic illness, relocation, and financial collapse. We'll put those ones in the next order. So this is just kind of helpful so we can see. So we'll have some trauma stuff and some non-trauma stuff. Sort of take a look at that. Okay.
Could you please repeat the order?
What's that?
Could you please repeat the order? Just
Yeah.
say it.
So I've got MBA, war.
War, combat. Okay.
Okay. And then SA, sexual assault,
Assault. Yeah.
and then disaster.
Disaster. Yes.
Okay. And then I've got
Infidelity.
break, ill, job, and money.
Perfect.
Okay. We can go to plots. We're going to do the same thing. We're going to put rating on the horizontal axis. You're going to hit add, continue, go to options, we'll ask for descriptive statistics and estimates of effect size. Again, we don't have to ask for homogeneity of the variance test because we don't have between subject factors, so we can leave that. Hit continue, and then paste. Okay. Go through and run this. New set. Okay. So we've got motor vehicle accident, combat, sexual assault, disaster, and then we've got infidelity, chronic illness, job relocation, and financial collapse, sort of ordered up. We've got our means. Yeah, Ignacio.
So you just gave a different order for pedagogical purposes.
Yes.
Right?
Yeah.
Okay.
Does it matter what order we put these in for this test? Does it matter? No, because there's no inherent order to this, right? We could scramble these around. I just sort of know what these data look like and think, okay, we kind of got this grouping and that grouping. So just in terms of kind of seeing what's going on for our graph, kind of put those in order. Okay. Who have I not picked on? Alicia, I haven't picked on you. Take a look at our means in our descriptive statistics. What are these means? What are you saying in these means?
They're pretty similar.
Yeah, they're really similar, right? And if you think about what we're actually doing within this design, so we've got an experimental session, or an experimental situation where I've got a group of people coming in, and I'm having them read a series of vignettes, and I'm asking them, hey, here's something terrible that's happened to a hypothetical acquaintance of yours. How willing are you, 0 to 8, to maintain friendship with this person after this horrible thing has happened? Right? What's a limitation of this study?
Someone's likely, so with all the scenarios being similar in a sense with a different factor differentiating between each one, there's probably some other variables.
Okay, so one, I think that's a good thing, right? So the extent to which people really do differentiate between different types of things and are willing to provide differences in friendship, right? So functionally what you're saying, Nick, is that the effect that I might be looking for, if there is one here, is gonna be pretty small, right? What's the other thing going on?
Just general rater bias.
Yeah, what's going on? What do you mean by that?
So there could be a couple of components. They could actually have a friend that has experienced any one of these things because you can do so many.
Okay.
They also don't want to seem like an asshole.
Yeah, exactly. I'm asking you, hypothetically, if you had someone who was experiencing some level of distress and hardship, how willing would you be in a hypothetical situation to provide friendship? What are people gonna, what is this whole thing pulling for?
Honesty. Or what do you want?
Be a good
What-
person.
What's that?
Be a good person.
Exactly. We got clear evidence of desirable response desirability, right? Like, oh, okay, God, screw that guy. No, 0, right? I can't be screwed. I can't deal with this, right? Like, what? You lost your job, man? I can't. It's gonna bum me out. 0, you're cut off, right? People generally aren't gonna do this, right? So we're asking people a question that has a strong potential for social desirability. On a 0 to 8 scale, probably everybody's gonna be scoring right near the top, right? And so when we look at these means, as Alicia noticed, like these are all super, super similar to one another, right? What does this suggest for our likelihood of finding an effect? Not great, right? So 1, we're looking for maybe a potentially a small effect. 2, we've designed a study that's pulling strongly for socially desirable response. And then we've got a lot of different things going on, right? So, like, at this stage of the game, stuff's looking pretty grim, right?
You should have used an implicit association test.
Shut up. Like, oh, magic one of those up, right? No, that is a good, you know, in terms of thinking about how we might do this, sort of start to work around and sort of maybe use now implicit sort of bias tests have their own sort of controversy and things like that, but that's certainly something that we could think about in terms of converging evidence. Yeah. What else?
So if we're looking potentially for like a very, very small effect, when you look, because I know we group them more by like trauma type stuff, the first 4, but the illness is the 7.6, and then 7.6, 7.6, 7.6, and then the other ones are more like 7, the lower 7s. So there might be something within those 4. That
Yeah, so there could be something, right? So maybe all is not lost yet, right? Chris, you want to say something?
Yeah, mine's a little, I just was wondering, is it infidelity like the person like cheated on someone else or someone else cheated on them?
I've got a friend, like you're my friend,
Uh-huh.
right? And you find out that Tara's fooled around on me, right?
Okay.
And how willing are you to continue friendship with me because I've gone through
Got it.
something
Okay.
difficult?
I thought it was the other way around. I was really surprised it was that high.
Okay.
Yeah.
Oh, how willing am I to maintain friendship with the person who screwed around on me?
Yeah.
Yeah, no, that's not the question.
Wow.
So for each one of these, the question is, I have a hypothetical friend
Got it.
who's experienced this stressor. And some of these stressors are things that we would traditionally identify as traumatic experiences. And some of these are very, very stressful, but probably not falling in the trauma experience thing. Yes.
Would you look at the between subject effects because of to see if there was variability?
Do I have a between subjects factor in this? Not yet, right? So hold on to that, we're gonna get there, okay? So, things are not looking great in terms of opportunities for me to sort of find differences here. But we're gonna ignore multivariate tests. We're gonna go down to tests of sphericity and ignore that because we assume we have a violation there anyway. But CJ, what's going on with our tests of within subjects effects?
We hit benchmarks of significant.
We do, right? And if I go through and I double click that, is that a small p-value?
Nope.
What's that?
No,
It's big.
small.
Small.
Well, really small. Yeah.
Right? So once again, thinking about P as strengths of evidence against the null hypotheses, incredibly compelling evidence for differences across these means, right? Power in this design.
Specifically.
What's that?
Repeated measures.
The repeated measures.
And then also, if we look at the variance in the sample, it's pretty clustered together.
Yeah, okay. So a couple of things. One of maybe the benefits of asking people questions that pull strongly for social desirability is everybody's pretty tight, right, in terms of stuff, right? So there's not a lot of variability there. So if we've got lower variability, it's going to reduce our error terms, right? One, we've got a really large sample. What's our sample size here?
230.
Yeah, 231. That's big, right? But then 3, again, we're using a repeated measures design, right? So it doesn't matter. Maybe, Chrissy, you're super nice. You're like, yeah, I'm going to go through and I'm willing to provide all these people, high levels of support because I'm in it to win it, because I'm a good guy, right? So in general, Chris's general approach to these questions is to generally rate them kind of high, right? Sean, on the other hand, is a jerk. Sean is a selfish person, and he's like, no, it doesn't matter which vignette you get first. You're like, I don't know, like 5 maybe, right? Sean's got a very different set point, right? But Sean's serving as his own control, and so if we're seeing the same shifts in Chris as we see as Sean, even though they're working at very different levels, what we've done is we've taken that individual difference and we've set it aside, and all we're looking at is relative to your own ratings, sort of how are things moving around, right? And so even though when we take a look at our overall mean values, these are all looking very close, right? If I've got a 0 to 8 scale, and I look at the mean values across each one of these things, and they're all right in that 7.5 rating, I should not be super excited about what's going to happen. But when we go down through and take a look at our actual statistical test, once again, these data are telling me that the likelihood of all these ratings being identical is functionally impossible, assuming that we've sampled adequately and sort of measured without bias, and things that we know that we haven't done, but still very compelling evidence, okay? How many people would I have had to have in a between subject design to tease out meaningful differences across means that are this close together? Tomorrow you're shaking your head. Why?
A lot.
I would have to have thousands of people if I were to individually sample different groups for each one of these, right? I would need 304 people in each group in order to detect sort of what these differences are. But here what I've done is I've got one sample that's quite large, but that design has been enough to go through and start to tease out these differences. Okay. Now if I go down and I look at my between subjects effects, this is, people are different, right? People start at different places. But I go down through and I look at my means, and again, well, that looks pretty impressive. Look at that, these little giant spikes, right? If I look at that, I'm like, yowza, lots of differences there. What's deceptive about this graph?
The scale.
The scaling, right? We're like, my low end is 7.1 and my high is 7.7, right? That's a super hyper zoom on this. If we were to go out and look at the whole scale, it'll look like a pretty flat line. It's a little bit of zigs and zags there. But again, I don't know exactly what's going on here. This is much more difficult to tease out than determine what's actually happening in these data, right? With our ordered means, it was easy. We could see, well, there's a nice ordered linear decrease over the course of time. Here, we're kind of all over the place, right? So we have to take a little bit different approach in determining our effect. Tells us that we have fairly convincing evidence against the null hypothesis that all of these means are going to be equal to one another. But I don't know exactly what one is different than the other one based on this. Okay, we're going to have to do some follow-up stuff. Questions about just the basic sort of omnibus test here? Feeling pretty good about this? Okay, cool. So let's go through and open back up to our examples here. So a couple different interpretations based on the analyses we just ran, okay? So for our inpatient depression, again, we're just focusing on the omnibus testing, so we're trying to give you language for this omnibus test. So we're saying results of the repeated measures of ANOVA provide the decisive evidence against the null hypothesis of equal depression scores across repeated assessments in a hypothetical population of individuals receiving inpatient care. P-value, yikes, that's tiny. S value, 471. Chrissy, what does that S value tell me? How would we interpret that?
The odds of finding this data by chance
Or
are.
that's BFB.
Oh, okay. Well, I gotta go through my prompts. But it's the coin flip one.
Yeah.
It's the odds of flipping a coin and getting heads 471 times in a row.
Right. So basically what this is saying, is what I'm saying with this S value, is the strength of evidence against the null hypotheses in these data is functionally the same as would be if you got evidence against a fair coin if you had 471 consecutive heads on a fair coin. Ignacio, if I flipped a coin 471 times and they all came up heads and I tried to tell you that that was actually a fair coin.
I just saw Batman, so I know the answer.
What's that?
I just saw this weekend Batman, the two faces.
Oh, right. So again,
It's very remote.
When we're trying to use it, and sort of the thing that we're trying to do with these is sort of just provide the scale of evidence against the null hypotheses here. And I don't even know what 7.90 times 10 to the 138th. That's not even interpretable anymore, other than to just see it and know. Yet it's functionally impossible. Yeah.
So I was confused. That's not the standard error, right?
No.
We don't have that formula for the homework.
Yes, you don't, but you had it. We had it last semester. So again, go back through those files in the lecture folder. It says 5060. Go to the t-test. It'll go through all calculation and things like that. Also, the Wilkinson article talks a little bit about that, how to interpret it, things along those lines. So that's what we'll find out. Okay. So, but notice here what I've done. I'm saying decisive evidence, and this is why I'm saying decisive evidence against the null hypotheses of equal depression scores across repeated assessments in hypothetical populations of individuals receiving inpatient care. This is me tying the whole problem together to saying, not just like there's evidence against the null hypothesis. Well, tell me, this is me saying that I know what the null hypothesis is, trying to put some meaning to that. Inspection of observed means indicates substantial reductions in depression scores over the course of intervention, right? It's just kind of descriptive. It's just me kind of saying what's going on with this, right? Here, trying to change things up a little bit, and I sort of like it when you guys are trying to change things up a little bit, just so it's not cut and paste the same thing. The test within subject effects of event identifies data from the current study as incompatible with the expectation of equal willingness to maintain friendships for individuals exposed to various forms of external stress. Right? And then we've got our p-value, our s value, our base factor. Not as big as this, but still really compelling. Right? Results suggest that specific events may influence others' willingness to provide and or maintain support following exposure to stressful events. Okay, so again, this is not a template, but just trying to give you language for how we can take what we got out of that omnibus test and package it in a way that conveys meaning without just saying it's significant, it's not significant. Question on the omnibus stuff. Okay, cool. Let's take a break and we'll jump into effect sizes and follow-up stuff when you get back. Okay, there we go. What is this not capturing in my partially squared? Yeah, this, right? And how much in these designs, how much variability is being sort of siphoned off as individual difference variability? A massive amount, right? And so the concern is, if I'm just running an partial eta squared in a repeated measures design, I've taken all this variability, this between groups error, right? And this is not stuff that we actually, I mean, we identified as between subjects error, but do we know why people differ on stuff? No, right? And so what we've done is we've systematically excluded in our repeated measures design all of that between subjects error, we've taken it out of the equation, right? And if we've taken 60% of the pie in terms of error and sectioned it off, what's that going to do to my partial eta squared? It's going to make it super big. It's going to look really, really impressive, right? But what we've done is we're systematically ignoring an entire different set of error variants that we're just pretending isn't there. We're just saying, well, that's individual difference error, and so we're going to ignore it, right? And so if I look at a partial eta squared in a repeated measures design versus a partial eta squared from a between subjects design, which one is going to be likely to be much, much higher? The repeated measure, right? Because the repeated measure's got a whole bunch of stuff that's just kind of hanging out there that we just kind of abandoned and left on the side of the road, pretended it wasn't there. I mean, we know it's there, and we systematically sectioned it off as between subjects difference and then set it over on the side. But the concern is that if I'm trying to compare effect sizes, right, from a repeated measures study and a between measures study, my repeated measures study effect is going to look much, much, much more impressive than my between subjects study, and then that's problematic. We've got an apples and oranges thing going on. And so partial eta squared is fine as long as I know what I'm talking about and interpreting it correctly. But if I'm just giving it the Pepsi challenge, right, between this and that, the concern is that my partial eta squared is always going to be, or the repeated measures effect is going to be much, much higher. Okay, people see what's going on and how we sort of systematically inflated our partial eta squared with these designs. Okay, so what we're going to do then, one of the options that have been put forward, and this is important for these types of studies, is calculating what we're going to call a generalized eta squared. Okay, generalized eta squared is an index that includes all sources of unexplained variance in the calculation. Okay, so we've got in this design we're calculating eta squared for our repeated measures effect, looking at the proportion of unexplained variability within the context of my within subjects assessment. We've excluded all of that, and in general, that's going to be a pretty big number, right? What generalized eta squared is going to do is going to work this back into the mix, so to give you an estimate that's a little bit, that's more comparable across between and within subjects. Okay. So our generalized eta squared, we can easily calculate this based on figures that are given in SPSS, but the tricky thing with generalized eta squared is that the specific calculation, the specific formula, is going to depend on your design, how many factors that you've measured, whether or not you have randomized factors or pre-existing factors and things along those lines, and which specific effect that you're actually looking for. Okay. So for our one-way designs, for our one-way repeated measure ANOVA designs are pretty simple, straightforward. What we've got is the sum of squares for our repeated measure over our sum of squares for our repeated measure plus our sum of squares for our between subjects plus our sum of squares error for the repeated measure. Okay, so what you're seeing is we're taking that between and adding that back into the denominator and sort of accounting for of all the unexplained variance in our model, what is attributable to our effective interest. Okay. People see the rationale for why we're doing this and sort of starting to make this in terms of a metric that's more comparable across both within and between subjects designs. Okay. And so in most cases, our generalized eta squared is going to be larger than our partial eta squared, our eta squared is going to be less than our generalized eta squared is going to be less than our partial eta squared in most situations, just in terms of what's getting added in. And just think about this mathematically, what's getting in and thrown into our denominator. As our denominator gets bigger and bigger and bigger, Sean, what does that do to our effect?
It's smaller.
It's smaller and smaller, right? And we all like big effects. We're all excited when we get big effects, but wanted to make sure that if we need to put our effects from my repeated subjects design in context with a different study that's between subjects, sort of making those start to be a little bit more comparable. Okay. Questions about this? Okay, cool. So again, generalized eta squares, attractive measure,